All right, guys. Hello, everybody. Welcome. I hope that you guys all had a nice weekend. I mostly had a good weekend. On Sunday, I climbed Mount San Jacinto. I don't know if you know, that's the one that is rising directly above Palm Springs. If you ever drove out east of town to Palm Springs, you would drive right by. It's a pretty sheer mountain, goes straight up, and you can actually take a tram most of the way to the top of the mountain, and they have a dining area there and everything you can just enjoy. But of course, I didn't do that. I started at the bottom. I walked for a long time all the way up, and you might notice I'm wearing a hat. I almost never have ever worn a hat before, except the problem was I got badly sunburned. So at 10,000 feet, even in October, I thought by October, this isn't summer, the sun's not going to be that bad. Well, I got pretty burned. And since I have so much hair to protect my head, it was not a good situation. So I might be looking like this for a few days now. But anyway, that was that. And then we played basketball yesterday. Fernando was there, and we had about 8 people. Next time, we need even more of you to come out. I will say that my trash talk was justified because I was on the winning team every game. So if anybody wants to challenge, come on out and join us. But we'll set that up again at some point. Yeah, so it was a good weekend. I hope you guys also had a really nice weekend. Let me just give you a quick update here before we jump in. There's no recap because we're going to start something totally new right now. So there is a homework assignment due on Thursday, and I realize if you look at the problems that I guess the last part of the assignment, we had kind of covered how to solve these non-homogeneous recurrence relations. So maybe you've had a chance to look at some of those. The rest of the assignment is about what we're going to do today. And it's generating functions. And generating functions, as it turns out, a lot of times you can do those problems without having to show a massive amount of work. So I expect that it won't be too terrible to get those done. If you need help with anything, of course, both today and on Thursday, I'm going to be around for office hours quite a bit. So I'm going to stick to my guns on the deadlines on that assignment. I think we should really try to get that done. With my help, of course, as much as you need. In addition to that, I had a panic attack a couple of days ago when I was reviewing where I normally am supposed to be at this time of the semester. Probably every professor goes through this with every class, but you're kind of looking and saying, oh my God, this is the start of the 9th week. And normally I'm supposed to be covering something else, right? And so I looked at it and I am a little bit behind. I think I just kind of went a little slow through some of that stuff last week, and that was good in a way, of course, because we could really dot our I's and cross our T's on everything, which I always like to do that. But because I got a little bit behind, I decided the best way to catch up is to ask you to watch a video, which is really just the lecture that I gave on this topic. When I taught it before, I had a pretty decent video of it. So if you don't mind, I sent you an email with a little link to a video. It's basically just a makeup lecture. I will tell you that later in November, we are going to be canceling a class at some point. So there is going to be a day when I'm actually not going to be around and we're just going to not have class. That's still a few weeks down the line. But I'll try to make up for asking you to watch a video now a little bit later in the semester. So by Thursday, and the other thing is many of you have figured out by now that I'm not real strict about deadlines. So, somebody will try to turn in a homework at 12:01 and I'll grade it and give them full credit. Then the following week, it's more like 12:30. And then the next week it's coming in at 5 a.m. So I wonder if he'll take this one. And then they try to turn it in 3 days late. I'm like, no, that's pushing it too far. Anyway, I am kind of flexible about that, as you figured out. But with respect to this video, I am going to be strict. And basically, I'm going to give you 20 points of free 20 out of 20 if you just get those video notes taken and scanned in by, I think I said noon, did I say? I forget what time I said, before class, right? The point is I need you to do this one on time. If you have to put the homework off and do that later in the evening, I'd rather have you do that, because the reason is that when you come in on Thursday, I would like you to have watched the video so that I can kind of pick up from that. I'll obviously spend a little time reviewing the highlights of the video. But please, this would be the one time I really ask you, really try to meet that deadline on Thursday noon or whatever it was. I forget what time I put, but it was sometime on Thursday before class. Does that make sense? Does that sound okay to everybody? Yeah, so I know I'm giving you a lot to do there, but I just want to try to get caught up a little bit. And that video is about graph theory. So it's just an intro video on graph theory. There's a lot of definitions. Draw some pretty pictures, think about applications of graphs and stuff like that. I think it's a fairly light type of video. You know, you could even pop some popcorn and invite some friends over and tell them you have a movie you'd like to watch. To see if they're still your friends at the end of the night.
It is almost Halloween.
Yeah, exactly. It's not a scary movie. At least I don't think it's a scary film. Anyway, yeah, so I really appreciate that. Okay, so that's kind of where we're at. We're about a month out, I guess, from our next exam. We'll probably have a quiz again, kind of about 2 weeks before that exam. So I would say roughly 2 weeks from now, we'll probably try and do a quiz. Lindsay, since I see you right now, can you stop by after class just to see me? Thanks. Okay, just want to make sure. Okay, so without further ado, I would like to cover a new section right now, and this is called 7.2. It's called generating functions. And this is a pretty neat topic in combinatorics that we have not had a chance to look at so far. And so I'm just going to start it from scratch right here. Generating functions. Okay, so what is this about? Well, this is yet another tool for solving counting problems. Okay, so this is a tool for counting problems again. And it's generally when you have like a whole sequence of counting problems. Counting problems for n equals 1, then n equals 2, then n equals 3. Just the same way as for recurrence relations. You have a whole infinite list of counting problems. And it is a synthesis of quite a bit of what we're going to see today, guys, is algebra along with calculus. So there's a fair bit of calculus. I'm not talking about super heavy calculus, but there's a fair bit of calculus in this as well. So let me write down the definition here of what a generating function is. This is just kind of by way of introduction. If we have an infinite sequence of numbers, so I'm going to do that. I'm going to start with h0, h1, h2, ... up to hn, and in theory it could go on forever. So let's let that be an infinite sequence of numbers. Okay, then its generating function. So we associate a generating function with a sequence of numbers. Its generating function is the series. We're going to be talking about a series here. And I'll write it as g of x. And so we're going to make a series, and the coefficients of that series are going to be the numbers in this sequence. So we'll have a constant term of h0, and then h1 times x, and then h2 times x squared, and ... Of course, the nth term would be hn x to the n, and ... It really could, in theory, go forever. And you know, it is also possible, I'll add a little note over here. It is possible for this series to be finite because you can just imagine that after a certain point, all of the terms are 0. And that would just give rise to a finite sequence of numbers that would then give you a finite series. Let's just make a note of that. So if the sequence is finite, so let's just say that, you know, we have H0, H1, H2, and dot, 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 up to Hn. Now, normally with our recurrence relations, they have not been finite. We've been mostly working with infinite series of numbers. But then in this case, we view this finite sequence as H0, H1, H2, dot, 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 up to Hn, and then 0, and then 0, and then 0, and dot, dot, dot. So in that sense, you could imagine that it does go on forever. Okay. So let's just try a couple of examples of writing down a generating function for a sequence. Okay, so I'll start you off with a sequence, and then we're going to try to calculate its corresponding generating function. So as an example, the generating function, here's a nice example, the generating function for the sequence. I'm going to make my sequence here. I'm just going to list some numbers, 1, and then 10, and then 45, and then 120, and then 210, and then 252, and then 210, and then 120, and then 45, and then 10, and then 1, and along. So if we had that list of numbers, so this is actually a finite example. Okay, so I've got roughly 10 terms here. So if that was my sequence, then the generating function for this sequence written in order is, I can just write it down. I'll start by just like writing it out explicitly. I'm going to call this G sub 10 of X. So we'll put a little 10 subscript on it. Don't really have to do that, but just as a notation, I think it's okay. So then what would the terms be? Well, it's very easy. You start with the first one here. H0 is 1, and then we would have 10x. And then we would have, the next term is 45x squared. And then we have 120x cubed, 210 times x to the fourth. We're just making a series by adding these terms together. 252 times x to the fifth, and then plus 210 times x to the sixth, plus 120 times x to the seventh. And then next would be 45x to the eighth. And the next one would be 10x to the ninth. And the last term would just be 1 times x to the 10th. So that would be the whole thing written all the way out. So that is your generating function. Now, I don't know, does that look at all familiar to anybody? Just curious if those numbers look familiar to you. The 1, the 10, the 45. They may or may not. If they don't, it's okay. Pascal's numbers from the Pascal's triangle. Yeah. I think you're onto something. I think you're onto something. Like, this is like 10 choose 0. The binomial coefficients, right? This is like 10 choose 0. This is 10 choose 1. If you think about 10 choose 2, 10 choose 2 would be 10 times 9 divided by 1 times 2. 90 over 2, well, that's 45, right? 10 choose 3, well, that'd be 10 times 9 times 8 divided by 1 times 2 times 3. Turns out to be 120. Absolutely right. So these are actually going to be binomial coefficients. And so this actually can be thought of as a summation. I'll write it in the summation notation here, with k going from 0 to 10 of 10 choose k times x to the k. Yeah, we could actually write the expression this way, okay? And that, in turn, resembles the more general binomial theorem with a y value already plugged into. Remember, the binomial theorem is like x plus y to the n. Well, in this case, this looks like we've already plugged in a 1 for the y variable. So I can actually write this as 1 plus x to the 10th. So in this example, I'm not saying in every example, but in this example, I can write my generating function in a very simple closed form. Okay, by just using the binomial theorem. It's because I've rigged this sequence, right? Those numbers are all just binomial coefficients that go into the binomial theorem. But normally, if this was just some random bag of numbers, then the first expression that I wrote down originally would be the best you could do, right? And you would just live with that, right? You wouldn't be able to clean it up into this nice simple form like this. But I just wanted to show you that sometimes these generating functions can be very simple, very easy to write down. In fact, that's often the power of these things. Let's take another example. So let's do, well, this would be a pretty easy one to think about. The generating function for the sequence. This time I really will give you an infinite sequence. The sequence is going to be 1, 2, 3, 4, 5, 6, and so on. Dot, 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 dot. And that goes forever like that. Okay, and so the generating function for that sequence is, let's see if we can just, I'm going to start by just sort of writing it out longhand. Just again, from the definition, you're just making a series where the coefficients of the terms are just indexed by these values. So we would have a 1, and then plus 2x, and then plus 3x squared, plus 4x cubed, 5x to the 4th, and 6x to the 5th, and this goes forever, dot, 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 like so. So that's what we would have here. It goes on forever. Okay, and so that is one way of writing g of x, but in a moment, we're going to see if we can find a clever way. This is never as good as you would like, because whenever you have dot, dot, dot in your answer, you're not really giving what's called a self-contained, like closed form of the answer, which is always what you would prefer. So, sometimes I like to write out the terms with dot, dot, dots just to kind of get a feeling for it in the first place. But in terms of a final answer, this is, although it's correct, it's also a little bit unsatisfying because of those dot, dot, dots. So the question is, can we like clean this up somehow? I'm wondering if anybody recognizes anything about these terms. Does it kind of remind you of anything at all, Kristen? It sort of looks like every one of these terms is what would have happened if you had taken the derivative of just a power of x, right? So like, exactly right. So I could think of this as, well, the 1 would have been the derivative of x. And by the way, I would like to just temporarily imagine that there was a 0 in front of this 1, because then I'm going to be able to put a 1 here. So what I'm going to try to do is take Christian's suggestion and express all of the terms of that series as being the derivative of some power of x. So the derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x, the derivative of x cubed is 3x squared. And so we see that indeed, if we look at those powers of x, we are really just taking the derivative of those. And this series that is inside of the parentheses here, 1 plus x squared plus x cubed, have we seen that this semester? Or do we know what it is? Because this is one of those, you better know it for graduation types of series, right? Yeah, this is the geometric series, exactly. This is a geometric series, and it's probably the most famous one where the coefficients are all just 1s in front of these terms. So does anybody remember what it actually could be written as?
It's like a fraction.
It's a fraction.
It's gonna be like 1 minus r.
What it is, just to remind you again, it's 1 over 1 minus x, okay? So if I whisper in your ear at the commencement, this is your answer. Okay, and then of course you have to take the derivative of that, because the derivative is still on the outside of it. So 1 over 1 minus x is equal to this infinite series on the line above it. Okay. Of course, we are viewing these as formal expressions in X. I don't want you to imagine that X has a numerical value. As soon as you start trying to think about numerical values for X, things start to go wrong. Because, for example, X would not be equal to 1 if we were trying to put it in the bottom of a fraction there, we would get 0. So this is literally just a formal expression. And literally that's what a generating function is. It's just a formal expression. Okay, it's not something that we're like plugging numbers in for X or anything like that. That's not the whole idea here. We're not actually evaluating these functions. We're really just using the generating function to separate out the different terms of the sequence by using these different powers of X. Okay, so it's just a way of representing things. Now, I'm pretty sure you guys can all take the derivative of this if we wanted to. We could use the quotient rule. For example, low d high minus high d low all over low squared. I'll let you guys check for me that this is actually just 1 over the fraction 1 minus x quantity squared. So that would be a closed form formula for this generating function. Okay, so it's kind of weird. The generating function for this sequence 1, 2, 3, 4, 5, 6, and so on is just this guy right here. Okay, so at least when you write it into a closed form formula. So far, kind of with me on this. Almost gotten through the first part here. What we've done in these first 2 examples is we've started with a sequence, and then we've written down the corresponding generating function. We could try to turn this idea upside down, and we could imagine that we started with by creating some function and ask whether it could be the generating function for something, and then ask what would be the sequence. So instead of starting with the sequence and creating the generating function, we can kind of reverse the philosophy and imagine starting with a function and then asking what sequence would that be the generating function for? Okay, so it would actually be pretty easy to create this kind of a setup. So we could, so in the above examples, we started with a sequence and produced its generating function. That was the idea here. These first 2 examples, that's the way we approached it. What I'm going to do now is try to reverse this process. So we can also reverse this process. Okay, so what do I mean by that? Well, I could, for example, what if I decided to take this function and just take the derivative of it? I could do that, right? I could try to take the derivative of that. So for example, let me just show you an example of this. If I took 1 over 1 minus x squared and I differentiated it, let's just run with this idea of using a derivative here. If you do low d high, you get 0 minus high d low. That's going to give you 2 over 1 minus x, and then divided by low squared. The low squared is 1 minus x squared, so you'll get a cubed on that. There's a double negative going on in that I've canceled, so you can just check me on this. This is actually what you would have, but we also know what this derivative has to be, because if we're taking the derivative of this, then that means effectively we're taking the derivative of this, which we can all do term by term. The derivative of 1 is 0. The derivative of 2x is 2. The derivative of 3x squared is 6x. The derivative of 4x cubed is 12x squared. Right? And keep going, write down a couple more. 20x cubed, and then 30x to the 4th, and dot, dot, dot. Right? So that would be it. And so what we could say is that So thus, 2 over 1 minus x quantity cubed is the generating function for a sequence that maybe we wouldn't have realized ahead of time. 2, 6, 12, 20, 30, and so on, kind of like that. By the way, if we wanted to, we could actually divide through by 2 everywhere here. So like if I literally divided this by 2, then I would get the series 1 plus 3x plus 6x squared and so on. I actually would like to do that. So I'm going to actually divide through, because I'd like you to see something. Divide through by 2 on everything. So on the left side, it becomes 1 over 1 minus x cubed. And on the right side, if I have now divided through by 2, well, this would be 1 plus 3x plus 6x squared plus 10x cubed plus 15x to the 4th and so on. And I wanted to do that because honestly, the numbers 2, 6, 12, and 20 don't really mean much to me. But the numbers 1, 3, 6, 10, and 15 actually do. Does anybody recognize this sequence of numbers here? The 1, the 3, the 6?
That's right.
It looks like numbers on a particular row of the Pascal's triangle, doesn't it? Right? It's exactly what it is. We could actually rewrite this as, like, for example, I know that 6 is the same as 4 choose 2. Right? 3 is 3 choose 1. 10 is 5 choose 3, and so on. So these are all just binomial coefficients. Whereas these original numbers are not binomial coefficients. Once we've divided through by 2, they actually are. So let me just rewrite this. This is actually 2 choose 2 plus, I'm going to write it this way, 3 choose 2 times x. And then the next one would be 6, which is 4 choose 2 times x squared. And the next one, which is 10, is 5 choose 2 times x cubed. And the next one, 15, that's 6 choose 2 times x to the 4th, and so on. And so on. So what that says is that, let's put it over here. We have actually found a generating function for, you know, n choose 2, basically. At least if we start with n equals to 2.
Dr.
So, right,
Annan, take
Yeah.
me with you.
Take me with you. Okay, sorry. Amber's in the Zoom today. You scared me.
You scared me. I thought you were gonna forget me.
Oh no, I'm not forgetting you. Okay, right, so in other words, what we have here, guys, is 1 over 1 minus x cubed. We can write it now. I'm gonna put it in a nice summation notation. This is a summation with n going from 0 to infinity of n plus 2 choose 2 times x to the n. Just check it out. If I plug in n equals 0, I get 2 choose 2. If I plug in n equals 1, I get 3 choose 2 times x. If I plug in n equals 2, I get 4 choose 2 times x squared. It's literally those terms over there. That's the ... version of it that we don't like so much. Now here we have a closed form formula for it right here. Okay, so I'm starting to wonder if I could, well, actually, let's actually pursue this a little further. I love this. Let's actually take this one and differentiate one more time. I would like to go with one more derivative on both sides. Okay, so let's try it. So let's differentiate again. On both sides. So on the left side, I will have 1 over 1 minus x cubed with a derivative on it. Okay. First thing I want to do is actually figure out what that equals. So maybe I'll put what it equals over here to the left. So I'm going to do low d high minus high d low all over low squared, just the quotient rule, right? So the low squared would be 1 minus x to the 6th on the bottom. So if I square the denominator, and then the low d high part, that's 0, and then minus the numerator times the derivative of the denominator. The derivative of the denominator would be 3 times 1 minus x squared times minus 1, because of the chain rule. We're using the chain rule in combinatorics today. So there's a little sign you have to put in there. So this is actually 3 on top divided by 1 minus x all to the 4th power. That's actually what we get when we take the derivative using the quotient rule. Remember, I said this is a synthesis of algebra and calculus. So here's a little bit of calculus. I'm just literally taking the derivative, right? You could ask your 150A students to find that derivative. That's what it is. But now what I want to do is also take this derivative term by term here. So I've differentiated the left side. Now I've got to do the same thing on the right side. So if I take the derivative on the right side, I'll have a summation n going from 0 to infinity. N plus 2, choose 2 is just a constant. And then the derivative of x to the n is n times x to the n minus 1. Just like that. Okay, and you can see right away that I don't need to start my summation at 0, because if I plug in n equals 0, that term is going to have a 0 on it, and so we can kind of just ignore it. So if you don't mind, I'm going to just start my summation with n equals 1 instead. So everything else, I'm just leaving it the same. Just going to start my summation with n equals 1. And now I don't like that form as a generating function, because usually it's supposed to be the powers are x to the n. So I am going to do a quick little change of variables here, and I'm going to replace that n minus 1 exponent with an m. So what you're going to notice then, if I do that, if n starts at 1, then what does the m start at? 0. So m would go from 0, still goes to infinity, of course. And I'm replacing, everywhere I see an n, I'm going to write it in terms of m now. So this n would be written as m plus 1, and then plus 2, and then choose 2. And then I have the n here, which I'm going to write as m plus 1, and then x to the m. So I'm just doing I'm not doing any serious math. I'm just literally re-indexing. I'm re-indexing this summation. Everywhere I see an n, I'm changing it to m plus 1. So change variables is essentially what that is. That's basically changing the variables on this. And so let's actually keep going. Something cool is going to happen. That's why I'm doing this. Let's just keep going here a little bit further with this. So this is going to be a summation, right? With m going from 0 to infinity of, well, this is really just m plus 3, choose 2. You see I have an m plus 1 plus 2. So that's m plus 3, choose 2. And then I have m plus 1. And then I have x to the m. And so I didn't really do a whole lot there. I basically just took the 1 plus 2 and changed it to 3. Now what I would like to do is, I'm going to keep working on this. We're going to get it even nicer. Remember that m plus 3, choose 2. That's really just m plus 3 times m plus 2 over 2. And then I still have m plus 1 here, and then x to the m. I'll start by writing it down like so. And, well, now I'm going to cheat a little bit. And I'm going to put well, this isn't too bad of a cheating, just put a 1 there. Okay, but I'm also going to put a 3 there. Now, I can't just do that. I cannot just do that. People are looking at me funny and they're right to be doing that because you can't just put a 3 there, but I could do it as long as I put a 3 on the outside. Now everybody's happy again. And why did I do that? It's because I see that on the top I have 3 consecutive numbers in a falling factorial pattern starting with m plus 3. And then on the bottom, I'm going 1 times 2 times 3. That is literally this part now, the way I have re-expressed it, it is just m plus 3 choose 3. That's all it is. So this is equal, my friends, to 3 times the summation, m going from 0 to infinity, of m plus 3 choose 3 times x to the m. 3 right here. And it just so happens, I know we don't like to have that 3 in front of us, but you know what? When we simplified the derivative over here, we actually got a 3 on top on that side as well. So we can cancel it again. Just like over there, we divided through by 2. Here, we can divide through on both sides by 3 instead. Let's do that, and I'm going to put the answer right here. We're just about done with this little calculation, but it's pretty cool what this is actually going to give us. So now I'm going to divide through by 3 on both sides. So on the left side, I will have 1 over 1 minus x to the 4th power. And on the right side, if I divide through by 3, I will have a summation where m goes from 0 to infinity of m plus 3 choose 3 times x to the m. Wow. Okay, so let's put a box here. And let's put a box. Oh, it's over here. Let's put a box on this one as well. Yes, Maddie. This one, I divided through and got rid of it. So basically that 3 canceled with the 3 over here, but I didn't like to write that on my notes because it looks bad. If I cancel it there, because it really should be there. So I just said divide through by 3 on both sides, basically. That's what you're going to get. Also, there's no reason why you have to live with m here. You can always rewrite it as an n again, because the choice of the letter of the summation makes no difference. So I'm getting a formula for 1 over 1 minus x cubed, and here's 1 over 1 minus x to the 4th. Let's just rewrite the one that we did earlier, the first one that we did, which was 1 over 1 minus x squared. I just want to recall it. It's right there on the middle board. That was this series right here. But you know what? I can write that differently. That series g of x, I can write it as a summation, n going from 0 to infinity of n plus 1 choose 1 times x to the n. Just make sure that you guys are agreeing with me on this, right? If I plug in n equals 0 here, I just get 1. If I plug in n equals 1, I get 2x. If I plug in n equals 2, I get 3x squared, and then 4x cubed, and so on. So that really is just this series written now as a summation. And so we have 3 boxes here that are basically giving us interesting formulas for generating functions for various binomial coefficients. And in fact, we can generalize this. And we can give a very general conclusion, which I'd like to do. If you guys will bear with me to write it down, I'll write down the general form. Because you know what I could do? I could have you differentiate this one. And then we would get another similar derivation of another generating function. So what I can do is just keep generalizing this. So I'm just going to say more generally, we can show, I'd probably show it by using induction. prove it by induction on whatever exponent it is, but we can show that if we take 1 over 1 minus x to the k, right? That if we do that, what we can do is we can show that that is equal to the summation as n goes from 0 to infinity. Let's see if we can figure out what it should be based on what we have here. Whatever the exponent is, kind of on the bottom of the left side, the coefficients, the binomial coefficients on the other side are like, what, you're adding one less than whatever power you have here. Are you noticing that? Right here, there's a third power on the bottom, and we're adding one less than that here. So this should be what? N plus k minus 1? Choose k minus 1? Is that right? And then that would be times x to the n. So this is a even more general version of what we've been deriving all along here. I know there's a lot of algebra here, and there's a lot of calculus that kind of went into this. But what the conclusion is, I would like to write this in words so we kind of have something we can sink our teeth into here. The conclusion from all of these calculations, because it's easy to get buried in doing the derivatives and simplifying the series and so on. But the conclusion is that g of x equal 1 over 1 minus x quantity to the kth power, right, is the generating function. It is the generating function for, well, basically for this sequence. This is the sequence, you know, k minus 1, choose k minus 1. And then the next term of the sequence would be k, choose k minus 1. And the next term would be k plus 1, choose k minus 1. I'm just increasing n, right? N equals 0. This is n equals 0, right? This is the n equals 1. This is the n equals 2. And then the next one would be k plus 2, choose k minus 1. That would correspond to n equals 3. And this goes on, right? Something like that. Notice on the bottom of these binomial coefficients is always you're choosing k minus 1, right? On top, you're allowing your n value to increase from 0 to 1 to 2 to 3 and so on, which is, of course, changing the number on top like so. But what that is, so this is actually something of some significance.
Is it Pascal? Like it looks like the iterative version of what Pascal is.
We are certainly looking at like a particular row of the Pascal's triangle, but I want to come back to these numbers.
Looks like stars and bars.
Amber, say it loudly because you're in Zoom.
It looks like stars and bars.
Did you all hear that? It looks like stars and bars. It is stars and bars. Remember, if you have n stars and there are sort of k bins, you would use k minus 1 bars to divide out the arrangement. And you'd have that many stars and bars added together, and then you would be choosing the bars, right? And stars and bars is, of course, used to solve a lot of problems that we've looked at. So these numbers, let's continue this conclusion over here. I want to add a little bit more to what I'm saying. Let's add a little bit more to this because this is a pretty, I was kind of blown away when I saw this. I'm like, how can stars and bars show up as sort of being related to taking a bunch of derivatives of 1 over 1 minus x? But that's essentially what we're observing right now. In a minute, I'm going to show you why it should not have been a surprise to me. Right? Actually, the first time I saw it, it was a surprise to me. I was like, I'm not going to see stars and bars if I do this. But then I saw it, and then I realized later why I shouldn't have been surprised. And I'm going to share that with you in just a moment. But before I do that, let me just continue this little sentence here. So what are all of these numbers? These numbers, I'll just say which forms the sequence that counts This is a sequence that counts the number of solutions to the equation x1 plus x2 plus dot 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 plus xk equals n in non-negative integer values of x sub I. So all of these x's are just non-negative integers. And if I asked you how many non-negative integer solutions are there to this equation, you've seen that before, right? There's n is the number of stars, right? Could be 18 pieces of fruit. And then these x's are telling you how many apples, how many oranges, how many cherries, and so on, according to the different categories, and it has to add up to some fixed total. So it's absolutely a stars and bars problem. So this is totally just doing it using algebra and calculus, that we have derived a generating function for the stars and bars series. Okay, this is of course for a fixed value of k, right? But then for any value of n, the different terms of the generating function, the different coefficients, right, are going to be the number of solutions to that stars and bars problem. Okay, so but I would like to think about this a different way, because again, I was shocked when I first learned this, and I was like, how is it that this has anything to do with stars and bars? It actually does make more sense than we might first realize. So to understand this from another perspective, I'll just put a colon here, and then I'm going to do my little spiel over here. I think I can fit this all in there. Sort of another way to think about this. If we look at 1 over 1 minus x to the k, which is, of course, front and center here in my generating function, we can think of that as 1 over 1 minus x times 1 over 1 minus x times 1 over 1 minus x and dot, dot, dot. Obviously, that would be happening k times. Okay, so we would have that like so. And we already know that 1 over 1 minus x can just be written as 1 plus x squared plus x cubed dot, dot, dot. And then again, the next 1 over 1 minus x is the same thing again. 1 plus x squared plus x cubed plus dot, dot, dot. And we have that each time. 1 plus x squared plus x cubed, and so on. And then there's a bunch of those. And then the last one, 1 plus x squared plus x cubed, dot, dot, dot. So it's a little bit to write that down, but that's what it would be. And we could ask ourselves, once we've written that down, we could ask ourselves, what would be the coefficient of x to the n? Now, we already know what the answer is. We already know that the coefficient of x to the n is right here, because we've already derived this box by using calculus and algebra. Okay, but let's try to understand from a totally different perspective why the coefficient of x to the n should be this thing right here. Okay, so if you need to, pick a value of n in your mind, maybe n equals 10. You say, how would I figure out the coefficient of x to the 10th in this expansion of this really cumbersome formula? Well, I'd pick some x's from here, and then I'd pick some x's from here, and I'd pick some x's from here. And I would do that up until I had a total of 10 x's chosen. So I'd be choosing some of these x's, some of the, after all, when you FOIL this out, you're going to be choosing one of these terms, one of these terms, one of these terms. You're grabbing a handful of x's from each of those factors, and you can take a total of, let's say, 10 of them, right? So it's really just asking, well, how many ways are there to sort of decide how many x's you want here, and then how many x's you want here, and then how many x's you want here. You're going to add those up, right? And it's got to add, and there's k factors here. So the last one would be x to the x of k. equals n. It is that equation that we were just referencing right here a moment ago. Yeah, does that make sense?
Yeah, so when we ask how many. If like x squared. One term. Right now.
Well, if I want to know what's the coefficient of x squared, I have many different ways of making an x squared after I FOIL this out, right? So, and I want to know how many ways can I do it. So I could pick this x and then this one and then this one and then this x here. That would be one way of creating x squared, right? But there'd be many others as well. Yeah. And so what this would represent, this would be saying I'm going to take one of those x's, none of those, and dot, 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 and then one of those, and then in that case, your n is 2. And this would be one way of, solving this equation in non-negative integers with n equal 2. Yeah, Nikolai.
Is it,
That is a different thing where you have, more variables in play. See, here we only have, as you can see, the binomial coefficients. So yeah, that's kind of a little bit of a different thing. So I was gonna write something else down about this. Let's just write down a quick note here for ourselves so we can look back at this later and understand this. If you FOILed this out, or if we FOIL this out, the coefficient of x to the n is the number of solutions to x1 plus x2. Let's use some different letters here. I'm going to use e1 plus e2 plus dot 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 plus ek equals n. And I'm using e's because e stands for exponent. This is like which exponents you're choosing, right? So the thing you really care about here when you pick a term is the exponents. So with e sub I greater than or equal to 0. That's basically what you're looking at. And so again, what is the coefficient of x to the n? Well, it's just this number of solutions. The number of solutions to this equation using non-negative integers, which is by stars and bars, n plus k minus 1, choose k minus 1. So I'll just say which is n plus k minus 1, choose k minus 1. So that's exactly what we derived right here. Let's just make sure the takeaway is clear. Everything on this 2/3 of the room is just algebra and calculus. I'm not creating a word problem. I'm not trying to do a counting problem. I'm literally just taking a series and taking derivatives and looking at the coefficients of it. And we derived this, well, we didn't really fully do it. We would have to actually prove that this is always going to work, but this is totally in a non-combinatorics derivation. This perspective here was literally just start with 1/1 minus x and start taking its derivative 3, 4, 5 times and start looking at what kind of terms you get. Okay, turns out the binomial coefficients were showing up, but this was mainly just an algebra and calculus approach. Then we started over and said, wait a minute, 1/1 minus x to the k can be thought of in this way, right? As a product of each of these infinite series, and thank you. In this way, the coefficient of x to the n here is more of a combinatorics problem. It's sort of saying I've got to figure out how many ways are there for me to grab some of these and some of these and some of these and some of these. These are apples, these are cherries, these are oranges, and I've got to have a total of n fruits at the end of the day. N stars, right? And k minus 1 bars. It really is that same old stars and bars problem that we looked at earlier. Okay, so I think it's just kind of neat to figure that out. Let's do, what am I doing on time here? Pretty good. Let's do a quick example. of a real problem that we could solve. Yeah, Nikolai, go ahead. It was more for this discussion. Yeah, exactly. Okay, let's try an example. I'll just squeeze it in here. So how about this one? So here's an example. For what sequence is the quantity 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th plus x to the 6th times x plus x squared plus x cubed times 1 plus x squared plus x cubed and plus dot dot dot. The generating function. So again, just to remind everybody, where this topic started today, I started you off by giving you a sequence and then we created the generating function. And then after we kind of did a couple of examples of that, I said, well, what if we turn this problem upside down? What if instead I start you off with the generating function and ask you, what is the sequence that is a generating function for? Right? And so the way that we might want to think about this is, well, what would be the coefficient of x to the n? Right? Because those are going to be that will be the nth term of the sequence. Right? So when I'm thinking about how to solve this, for the solution, what I want to do is figure out, well, what would be the coefficient of x to the n? So this is where the guts of the problem really is. Well, wouldn't you agree that I'm really asking for how many ways are there to buy n pieces of fruit? If you can buy at most 6 apples, you must buy 1, 2, or 3 oranges, and you can buy any number of cherries. It's really a stars and bars problem with constraints, right? So you're looking for a coefficient, but now this time with constraints. We can't buy more than 3 oranges. Have to buy at least 1, can't buy more than 3. And the number of apples is at most 6. So what we're really looking for is the number of ways. So let's just say it this way. This is the number of ways. This is the number of ways to solve E1 plus E2 plus E3 equals n. The e's are the exponents that we're going to pick. And we can obviously see the constraints here, right? The constraints are that, well, E1 has to be no more than 6. So it would be between 0 and 6, the first exponent. The second exponent would be between 1 and 3. So E2 is between 1 and 3. And then the third exponent, which is E3, can be anything greater than or equal to 0. So it's just how many ways can we solve this stars and bars problem with n stars initially, with these constraints on the variables that we're choosing. Okay, so well, how do we do these kinds of things? You might remember that if there are any, sometimes we had to have at least a certain number of apples and at most a certain number of oranges. Whenever it was at least, like here's the one I'm mainly focusing on, I have to take at least 1 x from here, right? And do you remember how we did that? We sort of just said, oh, well, I'm going to go into the store and grab the 1 orange that I'm required to take and then start over again, right? So you could actually imagine doing that. So what we could do is we could kind of replace this I'm not gonna formally change the variables here, but I can replace this with E1 plus E2 plus E3 equals N minus one less star. But now my constraints would be, okay, E1 is still limited from 0 to 6, but now E2 would be limited between 0 and 2. Instead of from 1 to 3, it's limited between 0 and 2. Good enough? And now you can kind of see that we're back to a pretty familiar problem. We're going to ask how many ways are there to solve this with no constraints, and then we're going to subtract violations. So we've actually done this part before a number of times. So let's just see how that might look, guys. If we don't have any constraints on the E1 and the E2, right, then would you agree that, so the answer here, the answer is going to be, and by the way, when I say answer, I mean final answer. Like we're already ready to do the final answer to this question. So without any constraints at all, would you agree I have N minus 1 stars? And how many bars do I have? 2, right? So this would be N minus 1 plus 2, choose 2. I'll simplify it in a moment. I'm gonna wait to do the simplifying. Then I'm going to start subtracting violations. Now, there are actually 2 different kinds of violations here. So normally we would create a couple of sets and we would subtract the set A, we would subtract the set B, and then there's the inclusion exclusion. So we'd have to add back in the intersections. I'm just going to do that without formally doing all of the inclusion exclusion.
Dr. Annan.
We're just going to do it kind of informally here. So this is how it's going to look. So there you go. That's N minus 1 stars, 2 bars. If I think about violations to E1, that would be, oh, if I have 7 or more apples. So that just means I have to subtract 7 out of the top of this thing. So minus 7 there. It's always going to be 2 bars. So I'll just go ahead and choose the 2 bars like that. And then the other possible violation would be if E2 was at least 3. So now we would have N minus 1 plus 2 minus 3, choose 2. And then we have double subtracted the case where E2 was at least 7 and E1 was at least 7 and E2 was at least 3. So I have to add that one back in. Okay, so I'm putting it back in, N minus 1 plus 2, and then minus, okay, if E1 is at least 7 and E2 is at least 3, that's 10 stars that I would be subtracting here and choose 2. And I'm just going to simplify this now, if that's okay. But if I simplify this, I get N plus 1, choose 2, minus N minus 6, choose 2, I believe. And then minus N minus 2, choose 2. And then plus N minus 9, choose 2. I better check my notes. Make sure I did that all correctly. Yeah, that's it. That is actually the correct sequence. So this would be your H sub n, right? So this would be equal to H sub n. This is the generating function for this sequence. So like, for example, 1 second, Christian, if n is equal to 0, right, then you can see that, well, the numbers on top are smaller than the numbers on the bottom. So that's just going to be 0. So in this case, H sub 0 is 0. You should not be surprised by that. Because if you multiplied this out, you would have at least 1x because of this middle term. Like this has no constant term. If you FOILed this out, you would have no constant term, right? What about if n was 1? Just kind of curious. If n was 1, what's h1? So if n is 1, then I have 2 choose 2. And the rest of these numbers are underwater. They're all too small on top. So that's just 2 choose 2, which is 1. There is only one way to get just an x out of this. And in fact, we can see it. We have to take that 1, we have to take that 1, and we take that x right there. Right? Isn't that cool? Let's try n equals 2. because I'm having fun with this. H2, what's the coefficient of x squared? Okay, so there's more than one way to get it. I first want to figure it out over here, and then I'm going to figure it out from my formula. So how could I get an x squared? I just want to brute force it. So one option would be to take a 1 and an x and an x. So maybe I'll write it down. A 1, an x, and an x. That gives me x squared. So I could take a 1 and an x and an x. How else could I get x squared? I could take this x, and then this x, and then this 1, right? Is there any other way to make x squared happen?
Take the x squared.
Take the x squared in the middle and a 1 on both ends. So a 1 and an x squared and a 1. That's 3 ways. Is there any other way?
That's it.
That should be it. Now let's work it out. What is H2? I hope it's 3. So if we put in 2 for n, I get 3 choose 2, which is 3. Everything else is underwater, right?
Oh, wait, no.
Yeah,
Oh, wait.
everything else is just going to be 0. So there you have it. So, you know, here you go. You're starting to build the sequence of terms of how many ways there are to do this. Okay, pretty cool. Let me show you just like one more problem that we could kind of set up with using a generating function. So I think there's one homework problem where it asks you to write a story. This is for Thursday's homework. It asks you to write a story where the solution to the story would be would be the generating function that they give you in the problem. So like my story here could be, I was asked to go to the store and buy at most 6 apples, between 1 and 3 oranges, and any number of cherries. And the number of ways of doing that would be spelled out by the generating function that's given there. So it's kind of an interesting. So that's an easy problem, by the way. That it looks bad on paper because they're like, what? I'm supposed to like come up with a scenario? Yeah, it's actually not so bad. So let me give you one more example. So in this case, so on this example, I gave you the generating function, and we had to kind of find the sequence, right? What about this one where I'm going to ask you to find the generating function? So find the generating function for the number of ways to select n pieces of fruit from apples, oranges, cherries, and bananas. Okay, if we must take at most 4 apples. Sorry, it's a little bit of writing here. Takes a while to write it out. At most 4 apples, at least 3 oranges. An odd number of cherries. That's a weird one. You have to take an odd number of cherries. Could be 1, could be 3, could be 5, could be 7. Yeah. Oh, at least, I'm so sorry. At least 3. Yes, at least 3 oranges. My bad. Thank you. At least 3 oranges, an odd number of cherries, and a multiple of 5 bananas. That's the whole question. It's a lot of. This is a problem where writing the question is way longer than writing the answer to the question. So you're seeing here that this is a question we wouldn't have asked before. An odd number of cherries and a multiple of 5 bananas, that does not sound like a problem we've ever looked at before. So somehow generating functions gives us a chance to kind of look at a more variable type of problem with this vine fruit analogy that we've used quite a bit. But guys, the thing with this problem is you can basically just write the answer down without any work and without really doing anything, because essentially what you're going to do, so they're asking us to write down the g of x, right? So aren't we just saying, okay, there's going to be 4 parts. There's the apple part, the orange part, the cherries part, and the banana part. The apples, it says at most 4 apples. Okay, well, that's going to be no apples, 1 apple, 2 apples, 3 apples, or 4 apples. All right, it is that finite series right there. That's the apples part. Okay. And then the oranges, it says at least 3 oranges. So that would be x cubed plus x to the 4th plus x to the 5th and dot, dot, dot. So we can just write that one down. Okay. And then the next one is an odd number of cherries. So that would be for the cherries, which I'll put here. We would have either 1 cherry, which would be represented with x, or 3 of them, or 5 of them, or dot, 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 an odd number. And then lastly, we have the bananas. And that would need to be a multiple of 5. So I either take no bananas, which would be represented with a 1, or I could take 5 bananas, or I could take 10 bananas, and so on like that. That would be it. You see, again, if you were wanting to know how many ways are there to select n pieces of fruit, you would be looking for the coefficient of x to the n. And that would mean you would grab some of these, some of these, some of these, and some of these, and you're just asking, well, how many different ways can you make those choices so that the powers of x add up to n, right? That's essentially what it is. And so this would be the answer. This would be the answer. If you foiled it, let's say n was, I don't know, 28. N is 28. I want to buy 28 pieces of fruit, right? The coefficient of x to the 28th in this expansion is going to be the number of ways that you could have picked one term from here, one term from here, one term from here, and one term from here as you foiled it all out, right? And so that would count the different scenarios that you could have, right? This would be a perfectly good final answer. Now, of course, we can clean this up. If we wanted to give a closed form formula, and I've got just a couple minutes, so I might as well. If I wanted to clean this up, we probably, hopefully remember the finite geometric series formula for 1 plus x squared plus x cubed plus x to the 4th would just be this much. Okay, and then on the second term, the second factor, I should say, I would pull out an x cubed from it. Because every single term in the oranges pile has at least an x cubed. And then after you factor out an x cubed, you just have 1 plus x squared plus x cubed. So that's 1 over 1 minus x. So I'll put that there. Okay. The next one is the odd powers of x here. I'm going to pull one of those x's out on top. And then what do you have left after you factor out an x from this? This would be x times, 1 plus x squared plus x to the 4th and so on. Well, that's again a geometric series, but instead of x, it's with a ratio of x squared. So this would just be 1 over 1 minus x squared. Right? And then this one is also a geometric series with the ratio of x to the 5th. So that's going to be 1 over 1 minus x to the 5th. So this is trying to get it into a closed form formula. And what you'll notice now is the 1 minus x to the 5th cancels. And So you end up with 4 powers of x on top if you want to simplify this. And on the bottom, what do I have? I have a 1 minus x. I have another 1 minus x. This actually factors as 1 minus x times 1 plus x. So that would be 1 minus x 3 times, and then a single 1 plus x. That look good? That would be, this would be another way to give the answer to this problem. That would be your generating function for this scenario. So here I've created a scenario and asked you to come up with a generating function. Like I said, in the homework, they're going to give you a generating function and ask you, I think they give it to you though in this form. And then they're going to ask you to write a story that would have that particular generating function, kind of turning the problem out. So that's my little crash course on generating functions, guys. What do you think? Any questions? Pretty fun. Okay. I like it. I like it. I like it. Okay. Guys, have a wonderful rest of your Tuesday. I'll be downstairs if you want to talk and ask any questions. I'll be glad.